Hello, today we're going to talk about the equations of static equilibrium for an extended body. So again, what is static equilibrium? Static equilibrium really applies to any object that is not accelerating. So if a body is not accelerating, it's in static equilibrium. And what happens when this acceleration is equal to zero? Well, we've got Newton's second law stating that F equals ma. If this term a, my acceleration, is equal to zero, then it follows that the force has to be equal to zero, or really the sum of all the forces acting on this body has to be equal to zero. We can also do the rotational version of Newton's second law, saying that the moment times the second moment of inertia times the angular acceleration is equal to zero. If our body's in equilibrium, the angular acceleration also has to be equal to zero. So it follows through that the sum of the moments on this body is going to be equal to zero. So these two things together are our equations of equilibrium that we're going to use. So when we've got an extended body in equilibrium, an extended body is any body that has mass distributed over some volume. So in real life, everything is going to be an extended body. Everything that exists has some mass and it has some volume. So with this, we've got the potential for these forces to act on different parts of the body, and because each of these forces acts on a different part of the body, they have the potential to exert a moment on the body. And so for a body to be in equilibrium, we need both the sum of the forces and the sum of the moments to be equal to zero. So here's an example of something we treat as an extended body. This is going to have, as is going to be a forklift, it's going to have some weight force pushing down here. We've got the weight of the boxes pushing down over here. And we're going to have normal forces at each of the tires. So each one of these, no matter what point we pick, there's going to be some moments in this because we've got not all the forces going through some central point. So with this, both our forces and our moments are going to be vectors. And that means that they're going to have some magnitude and some direction. And so each of the vectors with this magnitude and direction, we need to take that into account. So over here, we've got a kind of a barrel sitting in sort of an L-shaped bracket. The weight force is going to be pulling straight down, but the normal forces at these angled surfaces are going to have kind of a diagonal direction to them. So we can't just add up the magnitudes. We also need to take into account the directions of all of these. And so we do this by breaking everything down into components. So if we break everything down into components, then we can treat it as scalar equations that we can solve. And so what the components means is we're going to break everything down into, for a 2D problem, horizontal components and vertical components. So part of that diagonal vector was going horizontally, part of it was going vertically. And if we solve each of these equations independently, then we're solving the vector equation. So for a 2D problem, we've got sum of forces is equal to zero. We break that down into the the horizontal components, which we usually call x, and the vertical components, which we usually call y. For a 3D problem, we've got three different dimensions. So x is going to be back and forth, y is up and down, and then z is towards you or away from you. And so to solve these equations, to solve the equilibrium equations, we're going to start by drawing a free body diagram. So we've got, again, our barrel and the L-shaped bracket here. We're going to draw the free body diagram. We take away everything in the background, free the body from its surroundings. So we've separated the background there. We draw in the forces. So we've got our weight force, Fa, and then we had 2 points of contact, Fb and Fc. Those are our normal forces. We're going to break everything down into components. So the Fa, we can just kind of leave it as it is. It's already a vertical component. And then the Fb and Fc, we need to kind of take away those diagonal components, or diagonal vectors, and we've got some vertical part and some horizontal part to this. And so if we've got angles theta and phi, then we've got, these are our magnitudes of the vertical and horizontal components. So once we have it in component form, we can sum each of these up. So summing all the horizontal components, I've got cosine theta times Fb, that's this part right here, and then negative cosine phi times Fc. Since this is going to the left, that's going to be negative, and our magnitude is cosine phi times fc. So the sum of those things, that's all the horizontal components, the sum of all those are going to be equal to 0. And we can do the same thing for the vertical components. Fa is going down, it's going to be negative. So we have negative Fa plus sine theta Fb. It's going up, that's going to be positive. And then this is the magnitude of that here. Sine phi times Fc. It's also going up, that's positive. So I sum these three vertical components. That's all we have in the vertical direction there. And we are going to set that equal 0. That's our second equation. So I can do this for the force equations. I can also do this for the moment vector, for our moment equations. And so the last thing is we're going to solve all these equations for the unknown forces. Once I have all my equations, I use algebra and say I don't know Fb and Fc. If I do know theta, phi, the magnitude of Fa, which would just be the weight of the barrel, I can solve for those two unknown forces. So determining the moment equations, this is kind of the second part, the new part for extended bodies that we did not deal with particles. So start with just kind of our diagram. Just like we had for the particle analysis, we're going to draw in the free body diagram. So here, in this forklift diagram, I've got the weight of the forklift itself. This Fr is the normal force on the rear tires. Ff is the normal force on the front tire. And then I've got Fb, which is the weight of the boxes. So I've got all of these different forces acting on my body. And then that's what I need for that. I didn't have any background to start with, really. Although really it'd be sitting on the ground. You're going to determine a point to take the moment about. So the moment is all dependent on which point you choose. And really there's no set point that you need to choose. You can choose any point, but you just need to be consistent in that. So it is usually a good idea to pick a point that's going to make your life easier. And so what makes your life easier is if we can get rid of a few of these forces and we don't have to do as many calculations of the moments. So I want to pick a point with some unknown force acting through it. So in this case, I'm going to choose the front tire, the point where the front tire contacts the ground, and call it point A. And I'm going to take all the moments about that point. So the moment is going to be the magnitude of the force times the perpendicular distance between the point I chose and the force. So I need to find the moment that each force exerts about this point A. And to do that, I need to do the moment arm times the magnitude of the force, and I need to be careful with signs. So a counterclockwise rotation, so this force Fr would kind of cause this whole thing to rotate this way. It's a clockwise rotation, that's going to be negative. Something like the weight force is going to cause a rotation counterclockwise, that would be a positive moment. So I need to be careful with those signs, because if I mess one up, it's going to basically make my equations invalid. So I draw in my distances. This is, again, perpendicular distances to this point. So dr is going to go with Fr. dw goes with force W, the weight. And dv is the distance to the center of the box force, Fb. Write out my equations. Set all of these moments equal to 0. So I've got Fr times dr, and that's negative. Again, it would cause a clockwise rotation. Fw times dw, so it's the magnitude of the force times the distance there. That would cause a counterclockwise rotation, so that's positive. And then negative Fb times dv is equal to 0. You'll also notice here I don't have anything on this Ff. And that's because my distance from point A to where this force acts is 0. So it'd be Ff times 0. And that's why I chose something carefully, because really, if I know the weight of the boxes and the weight of the weight and center of mass of my forklift, the only thing I don't know is this Fr. So I've got one less unknown in this equation because I chose that point A. So once you have all your equations, then you're going to try to solve the equation. So you can combine this with your existing equations, the sum of forces in the x and the sum of forces in the y, and you're left with the equations that you can solve. So moving on to 3D problems, it gets a little more complicated. So we draw the free body diagram again, same thing as we had for 2D problems, and this is to determine them. We want to determine the point that we're going to take all the moments about. Again, we want to choose a point that'll make things easier later on. Choose a point that we've got some unknown forces acting through. Once we do that, we need to find the moment each force exerts about each coordinate axis through that point that I chose. So if I've got some point in space over here, I'm going to imagine orienting myself. So first I'd get the x-axis, and I imagine looking straight down the x-axis, and basically draw this whole thing as a 2D problem, imagining I'm looking straight down the x-axis. I do the same thing, except I take the y-axis, and I imagine I'm looking straight down the y-axis, and do the same thing, imagine I'm looking straight down the z-axis. And so in each of these different situations, I'm going to find different moments, and that would be the moment about the x, y, and the z-axis through that point. And then I'm going to solve those 3 different moment equations. The sum of all those moments and each coordinate axis is going to be equal to 0. Again, be careful with signs. A clockwise rotation about that axis is going to be negative. A counterclockwise rotation or moment is going to be positive. So set the sum equals 0, and we've got our 3 possible moment equations. So overall, in 2D, for an extended body analysis, we've got 3 possible equations. So we've got sum of forces in the x is going to be equal to 0. Sum of forces in the y is going to be equal to 0. So that's forces in the x and y. And then I've got 1 moment equation. And for a 2D problem, if you imagine x is going this way, y is going this way, really looking at the 2D problem, the z-axis is pointing straight towards me. So I'm taking all the moments about the z-axis. So that's my 3 equations there. If I go to a 3D problem, I have 6 possible equations. So sum of forces in the x, sum of forces in the y, just like I had for 2D. But now I've got a 3rd dimension. I can go away or towards someone. That's sum of forces in the z. And for the moments, I've gone from 1 moment equation to 3 moment equations. So the moments, imagining I'm looking down the x-axis, moments imagining I'm looking down the y-axis, and moments imagining I'm looking down the z-axis. So 2D problems, 3 equations, I can solve for up to 3 unknowns. 3D problems, 6 equations, I can solve for up to 6 unknowns here. So with that, that's all I have for this video. Thanks for watching, and I hope to see you again.